What's up guys, welcome to the second part of the level 7 in 7 hour series, where I gave you a complete tutorial on an IB subject in 7 hours. In this video, we'll be covering topic A2, networks. Starting off with A2.1, we have network fundamentals. In this subtopic, we'll be covering the basics of how networks are made. Before we start, let's define what a network is. So what is a network? A network is simply just two or more devices which are connected in some way. These connections allow for data to be shared and enable communication between devices. To give you an idea of how important the concept of networks are, here's a bunch of examples of networks in real life. Networks can range from covering small local areas all the way to spanning the globe. Smaller networks might include your school or an office, where different entities are part of that organization's network. Control systems, which we learned from A1, can also use networks so that devices over long distances can communicate, such as in a traffic light system. But these are examples of teeny tiny networks. A bigger network you're definitely familiar with is the Internet, which is just the name for the global network of computers. Within the Internet, there's the World Wide Web, or WWW, which is the term for the global array of all websites. There's also mobile networks, which use those big radio towers so that you can send SMS and make calls. Nowadays though, there's a lot of services which use the Internet for texts and calls, and your network provider probably gives you an Internet connection with cellular data. Cloud computing is when computational resources or services are accessed online through the Internet. Things like software as a service, platform as a service, and infrastructure as a service, which we also covered in A.1, are all reliant on the Internet to work. In simpler terms, stuff like Netflix, Amazon, or Zoom wouldn't exist without the Internet. Distributed systems are systems that are run simultaneously by multiple computers to make the system more fault-proof. These computers need networks to communicate with each other at high speeds. Distributed systems often also use edge computing, which refers to bringing systems geographically close to the locations they operate in, which usually results in less latency. So now that you understand how important networks are in the modern world, let's begin to understand how networks actually work. We'll start with different types of networks. Firstly, we have a local area network, or LAN. This is a network where devices are connected using wire, and is usually seen in offices with desktop computers. A more modern approach uses WLAN, or wireless LAN, and this is a network that your home network or school uses. If you ever connected to your school Wi-Fi, you are connected to their WLAN. Either way, they're both local networks that cover a small geographical region. You can connect LANs to each other across a large geographical area to make a WAN, or wide area network. The Internet is an example of a WAN and is the biggest one of them all. There's also a personal area network, or PAN. These are very short range, only limited to a small region around its origin, with its origin being usually your personal computer. Bluetooth is a prominent example of a PAN. Lastly, there's also virtual private networks, or VPNs. This is a special kind of network, because it's not really a network in itself. It's more like a tunnel through the Internet that exclusively connects two LANs, making them feel like one. For example, Lastly, there's also virtual private networks, or VPNs. This is a special kind of network because it's not really a network in itself. It's more like a tunnel through the Internet that exclusively connects two LANs, making them feel like one. For example, in this diagram, this LAN in America can connect with this LAN in Australia, creating this sort of tunnel through the Internet. This tunnel joins the two networks together and makes sure no one else can intercept the data being sent between them. Now let's explore what a typical local area network is actually made of. The first is a network interface card, or NIC. This is a component in a computer that allows for communication in a network. If you're using a laptop or phone, this was probably integrated into the device for you. The next two components are all used to facilitate communication within a local network, starting with the wireless access point, or WAP. This is what allows for wireless connections to the network. Of course, this isn't required, but you would then need to link every device using physical wires. Then we have a switch. A switch is a device that routes data within a LAN to the destination devices, meaning that devices within a LAN can communicate. With these components so far, it's possible to make a local network already. But what if we wanted to connect the LAN to the Internet? Then we need more components. Firstly is a router. A router's job is to direct data between networks. It's basically a step up from a switch because a switch is limited to one network and its connected devices. A router can essentially connect the local network to another network, in this case, the Internet. Next up are hardware firewalls. A hardware firewall filters incoming and outgoing data to and from the network, keeping the network safe. Another device used is a gateway, which acts as a translator of sorts to facilitate communication between the internet and your network, making sure that the components of your network can understand the data coming from the internet. Finally, there's a device called the modem, which connects your network to an internet service provider, or ISP. By connecting to an ISP, they can then give you access to the internet. These four devices are usually combined into one box that's collectively called a router, like your home router. These four devices are usually combined into one box that's collectively called a router, like your home router. But inside of your home router lies not just a router that routes data, but also these three components. Through these components, a local network can be part of the wider global internet. Moving on to network protocols. A protocol is defined as a set of rules for data transmission. From local networks to the internet, we can't guarantee that every computer will automatically know how to interpret messages sent from another computer. This is why protocols are so important. It allows all kinds of computers to communicate successfully. Here's a couple examples of common protocols used in networks. The TCP and UDP protocols are both used to ensure reliable data transmission. They're responsible for making sure the data being sent between computers are correct and ordered. We'll get into more details about reliable data transmission later. These next three protocols are all protocols that are specifically made for certain applications, unlike TCP and UDP, which are more general protocols. For example, Hypertext Transfer Protocol, or HTTP, is used to facilitate the transmission of web pages. HTTPS is also just HTTP, but with extra security features indicated by the secure in S. Dynamic Host Configuration Protocol, or DHCP, is used to facilitate the transmission of something called IP addresses, which is basically an identifier for all devices on a network. We'll also cover DHCP and IP addresses in more detail later in the video. Now let's move on to something called the TCP/IP model. The TCP/IP model is the backbone of data transmission. It's the common framework that is used every time data is sent through networks, whether that be LANs or WANs. It consists of 4 layers: application, transport, internet, and network interface, or sometimes just called link. Here's a summary table describing the layers of the TCP/IP model. To explain the model simply, think about how something is delivered in real life using something like FedEx. They could theoretically ship the item without any pre-planning, packaging, or labels, but that would introduce a whole lot of potential problems. What they do instead is take your item, slap a whole lot of package information on it, like the destination address, package number, or a certified stamp, and then put your item in a box and then deliver it using a secure vehicle. This sort of shipping process is basically what the TCP/IP model describes. The first layer of the model, application, is responsible for providing services that allow communication over a network. This layer is what allows the user to actually send and receive the things it wants. Think of it like placing an order into a delivery service. The network has all these tools to get you data, but it needs to know what exactly to send over. Protocols like HTTP, HTTPS, and DHCP are responsible for this, as they transmit information about what the user wants. The second layer, transport, is responsible for reliable and safe data transfer. It does this by attaching additional information to the data, like sender, receiver, error checking codes, and the protocol that the data is using. The TCP and UDP protocols are usually the protocols used here. The next layer is internet, which is responsible for finding routes for data to be sent through. This layer is when most of the workload starts to be driven by hardware. For example, the router is the main man behind this layer, as it does all of the calculations behind finding routes. Hardware firewalls make sure that data going through networks are safe, while gateways allow communication between different networks. Finally, there's a network interface layer. This is where the data actually gets sent from one device to another. Hardware like the modem, network interface cards, wireless access points, and switches are in this layer. The reason switches are in the network interface layer and not the internet layer is because the internet layer works with IP addresses, which is a unique address for all devices connected to the internet. Switches, however, work with another kind of address called a MAC address, which is a unique address for every device regardless of if the device is connected to the internet or not. And these addresses are usually given by the device's manufacturer. These layers work together to package data and prepare it to be sent without problems. We'll cover this in more detail when we get to the topic of packet switching. Now let's move on to A2.2, network architecture. In this subtopic, we'll be covering how networks are organized both locally and in wider contexts. So let's start with local network organization, beginning with network topologies. A topology just means a layout to arrange devices in a network. There's 3 main topologies you need to know. Firstly is star topology, where all devices are connected to a central hub. This hub is responsible for managing all traffic within the network and it must direct all data to their intended destinations. This hub can either be a switch or a router. Another type is mesh topology, where all devices are connected to each other. Instead of all traffic being routed through a central hub, data is just sent directly to the destinations from one device to another. Finally, we have hybrid topology. This is exactly what it sounds like, a mix of the two previous topologies. Here's an example of a hybrid topology. You can see these hubs are all connected with mesh topology, but each hub then manages its own group of devices, like so, and these are arranged in star topology. Each topology has its own benefits and use cases. Star topology is very cost-effective and simple to implement, and it works well for most small networks. Your home network is an example of star topology. All devices are connected to the home router, and the router then connects every device to each other and to the internet. Also, star topology is easy to scale up. Need more power to host more devices on your home network? Just buy a beefier router. But when networks get too large, a single hub can be insufficient to handle every request, which can cause the network to slow down. This is when mesh networks can be better. Mesh networks have higher transfer speeds than star networks because data is sent directly to its destination. There's also less data collision because data isn't concentrated into one single region, like it is in star topologies. All of this makes mesh topologies more reliable, but the setup can be quite more complicated than star topologies. And lastly, hybrid topologies just combine the advantages of each, making it both reliable and cost efficient, although the logistics behind setting up a hybrid topology can be quite complicated. Now let's talk about the concept of network segmentation. Segmentation refers to the division of a LAN into smaller sections. This can be either physically, like rerouting the wires through a process called VLAN, or logically through subnetting. The difference between them is that VLAN works on the network interface layer, meaning that it physically divides the network. Subnetting instead works on the internet layer, meaning that it uses IP addresses to prevent access to certain parts of the network to certain users. There's a lot of benefits to doing this. Firstly, it improves network performance and reduces network congestion. It also increases security due to the limited access and makes the network as a whole much easier to manage. Here's an example LAN, and I'll show you how we can implement network segmentation here. So here we have a double star network, where devices are connected to a switch, and each switch is connected to their own router. Using segmentation, we can divide each switch and its connected device into their own sections, like this. So this will be isolated like this will be like that, and this will be grouped here, and we can group these like so. Now each switch is essentially isolated into its own network, and if a device, like this one, tries to communicate with another device, say for example this one, it wouldn't work. This example can be something like an office, where each switch represents a different department of the office. So for example, this can be finance, this can be marketing, this can be HR, and so on. Segmentation ensures that each department's files are private and only accessible by the users within that department. Let's now move on to organization of wider networks, with the internet being our primary focus. Firstly, let's talk about the client-server model. All devices on the internet can be classified as either a client or a server, or both. We'll see why it could be both in a bit. A client is a device that sends requests to servers, while a server listens to and responds to requests. So here, a client might send a request like this, and the server just sends back an answer like so. Here, a request is a signal that tells the server that any client wants a piece of data that the server holds, whether that be a file, web page, email, or any kind of information really. We'll go over some examples of common servers. Chances are, if you use the internet, your device has probably used all these servers before. Firstly, a file server hosts files for clients to view or download. Whenever you download software onto your computer, you download straight from a file server. File servers can be scaled with more storage or more network bandwidth. To secure the server, access levels are usually implemented so that only administrators can edit files, and all files are encrypted while being sent. Next up is a mail server. A mail server manages the exchange and storage of mail between recipients. Every time you open Outlook or Gmail, for example, the mail server checks if you have new mail, and if you do, it pops it into your inbox for you. Mail servers can be scaled with more servers, so that each server computer handles less users at a time, which decreases latency for every user. They also need to protect themselves and their users from spam, backdoor access, or phishing, which is when users are tricked into doing something, like giving up their login details. For this, spam and phishing filters are implemented, and secure authentication methods prevent any form of unauthorized access. Web servers are next, and these host websites. All websites are made of code called HTML, and whenever you want to visit a website, the web server sends your computer the HTML code for the website through the HTTP protocol. Like mail servers, they scale with more server rooms. To protect themselves, web servers usually use firewalls to filter malicious requests or use the more secure HTTPS protocol. All these servers are critical in modern everyday computing. This is why all of them likely use redundancy servers, which are duplicate servers that act as a backup for the main server. If there is something like a power cut, the redundancy server takes over until the main server's issue is fixed. The next few servers aren't as intuitive as the last three. A proxy server is a server that sends requests on a server or client's behalf. This allows the original client or server to mask their IP address online, as everyone else only sees the proxy server's IP address, providing anonymity when using the internet. It scales with more server rooms as it can handle more users at the same time. A domain name server, or DNS, is sort of like a phone book for websites. For example, a web server might serve the actual HTML code for the websites, but how do you decide which of the billions of web servers to actually go to? When you enter a URL into your browser, the URL first goes to the DNS, which then looks up the corresponding IP address for that URL. That IP address directs you to the correct web server, which then gives you the website itself. The speed of your internet browsing is therefore directly affected by the speed of your DNS, so multiple server rooms are needed to accommodate every user and reduce latency. DNS servers are also a prime target for malicious activity, where hackers can hijack the server to misdirect users to where the hackers want. To fix this, outputs need to be verified, often by using a process called DNS-SEC. Lastly, a DHCP server is responsible for assigning IP addresses to devices that join a network. Whenever you connect to a network, it's this server that gives you an IP address. These servers are built into most routers, like your home network. To prevent any unusual IP assignments, DHCP users use access levels and authentication, like administrator permissions. Just like the first three servers, these servers are used very frequently in modern computing. All of these servers often use redundancy servers to continue operation even if the main servers go down. The client-server model is one way to link different devices on the internet. Another way is through the peer-to-peer model. This model is where every computer is linked to every other computer. You can think of the structure of a P2P network like a mesh network, and a client server as a star network. In practice, this means every computer acts as both a client and a server for all other computers. The best example of this is torrenting. When you want to download a file through torrenting, maybe through some illegal means that I don't condone, you're connected to multiple different computers through the internet, each holding different parts of the file. Your computer then downloads bits of the file from multiple computers at once, like filling in puzzle pieces. At the same time, you're also supplying new computers that enter the P2P network with your bits of the file that you downloaded. Now that you have an understanding of both client-server and P2P, let's compare the two network organization methods. The client-server model is the most widely used on today's internet, and that's for a good reason. It provides a single point of access for services, making it easy to set up, scale up for businesses, or to implement advanced security methods. Servers are also specializable, meaning they can be customized so that they're really good at one thing, like serving mail, websites, files, or movies, just to name a few. There are some problems with the client-server model though. Because it's one point of access, it's also one point of failure. If the server's power goes out, or if a server gets attacked by hackers, the entire service shuts down for all clients. Servers are also quite expensive to start up and maintain, making servers not a feasible option for some. Now moving on to P2P. Firstly, P2P is decentralized, meaning there's no central entity that oversees all traffic. This improves privacy of individual users and makes it so that there's multiple points of failure. This means that if one device on a P2P network goes down, it doesn't hinder the performance of the rest of the network. P2P also scales off the number of users, so while more users usually mean more lag in client-server models, it actually makes things faster in P2P. This is because the server's total computational resources increase as more users join. And since each computer contributes its own resources, there's very little to no costs. P2P is used in stuff like torrenting, blockchain and crypto, and VoIP, which underpins voice calls. But because of the reliance on users, a P2P network becomes quite slow with few people in the network, making it quite unreliable. Also, since P2P connects devices directly to each other, there's no central security system in place, meaning it's easy for anyone to breach into another device within the network, making it insecure for ordinary users. Now we're going to move on to A2.3 data transmission. Firstly, let's talk about mediums of communication. This is referring to how data is physically sent from one location to another. There's fiber optic cables, which uses light signals within the wire. These wires have long range, fast speeds, and are hard to intercept, but they're also quite expensive and hard to set up. There's also twisted pair cables, which uses electrical signals. You can think of these as a level down from fiber optic cables. They're easier to set up and are still reliable, but in terms of performance, it's a direct downgrade. Finally, we have wireless. Wireless uses radio waves with different frequencies to transmit data. It's the most flexible and simple to implement, making this the go-to option for most home or school networks. However, it can have bandwidth issues, has low range, and it can be accessed by anyone, even unauthorized users. Now let's dive deeper into IP addresses. We've glossed over what they are, but for a more concrete definition, an IP address is a unique identifier for a device on a network. They come in either IPv4 or IPv6. IPv4 is a series of 4 numbers ranging from 0 to 255. You're probably familiar with this kind of IP address. A total of around 4.3 billion unique addresses can be made with IPv4. It might sound like a lot, but soon IPv4 addresses on the internet might all get used up, which is a big problem. IPv6 is the most promising alternative. It's made up of 8 4-digit hexadecimal digits, making around 10 to the power of 38 unique addresses. Around 40% of all internet traffic is done with IPv6, but as of 2025, full integration to IPv6 hasn't been achieved yet. There are also static and dynamic IP addresses. A static IP address is a fixed address that never changes. These are used by servers because the same IP address should be used every time a client requests data from a server. A dynamic IP address is one that changes, either every login or after a certain period. Clients usually use dynamic IP addresses, like your personal computer. This is to keep unused IP addresses open for later devices and to make address organization easier. IP addresses are further categorized by private and public IP addresses. A private IP address is an address that is only visible within a certain local area network, while a public IP address is an address visible to everyone on the internet. When you connect to your home router, you're assigned a private IP address unique to your computer, like these addresses here. A public IP is the IP of your local area network and is visible to everyone on the internet. You can think of it as the IP address of your router. But it turns out, nobody on the internet can actually see your private IP address, because that's hidden by your router. Only the public IP address that your router holds is visible. This is called Network Address Translation, or NAT. It lets every device that's connected to a network share the same public IP address. When data is exchanged with the internet, the other entities route the data to this public IP address. You can think of this like a household sharing the same house address, but everyone living in the house has their own room. When things are sent to your house, it's shipped to your house's address instead of the exact person's room that it's for. This model has several advantages, being that it uses public IP addresses efficiently, and it improves security for individual devices, as your router can block bad actors from entering your network. Let's now expand on how data is sent through the internet. We already covered the basics when we learned about the TCP/IP model. Data is processed through 4 layers, with each layer serving a different purpose in transporting the data successfully and reliably. What I didn't mention is that when data is sent, it's actually broken up into smaller units called packets, and are sent using a process called packet switching. Here's how it works. You start with the application layer. Here you want to send an email to a friend, so you write the message and it's ready to be sent. Now in the transport layer, data is broken into packets. Each packet is made up of a header and a payload. The header contains control information, such as packet number, source IP, destination IP, error checking codes, the protocol it's sent through, meaning TCP or UDP, and the time to live, which defines how long a packet can go unreceived without self-terminating. The payload then contains the actual information to be sent. In the internet layer, a router decides which path to the destination each packet takes. Not all packets have to take the same route. In fact, different packets usually take completely different routes. So say you're here in America and you want to send an email to this guy in Russia. The packets could either take this route like that, or this route like this, or this route like this, and so on. This means that even though the packets are sent in order, almost all the time they're not received in order. At the destination, a switch is responsible for forwarding the packets to the correct device on the network, where the packets are reassembled into the correct order, which forms the correct message. That is what gets popped into the recipient's inbox. Now let's dive deeper into the concept of routing. Routing simply refers to the path data takes through a network. It's why a router is even called that in the first place. As we've seen, data can take multiple paths to its destination over the internet, and it's the same concept in local networks too. Data is sent through multiple different devices before reaching its destination. But in local networks, the routing can either be static or dynamic. In static routing, the routes that data takes are predetermined by the network administrator. This means that every possible route is considered and accommodated for. Dynamic routing is more like how it's done by a router. An algorithm is used to calculate the fastest possible route. Ultimately, it's up to the local network administrator to decide which to implement. Generally, static routing is simple to implement, uses minimal bandwidth due to no calculations being needed, and is consistent in its speed. But as a network grows, it can become troublesome. Every time a new user is added, additional work is required. It's also vulnerable to unexpected errors, and these issues only get worse as the network grows larger. Hence, static routing is best used in small, fixed-size networks. Dynamic routing, on the other hand, scales well with larger networks. This is because it doesn't require any additional work for new users, and also avoids errors in the network. It does, however, take up more resources due to calculations, and the initial setup can be more complicated. So dynamic routing is best used in larger networks. And that's done for A2.3. Lastly, we have A2.4, Network Security. Here are some of the basic security measures in place to protect networks. We've seen two of these already, firewalls and NAT. As a refresher, a firewall monitors and filters incoming and outgoing traffic from a network, and NAT is a system to hide individual computers' private IPs from the internet by grouping them under one public IP. We haven't talked about the other three yet, so let's go over them. Encryption is simply the act of scrambling a message. This means making data unreadable to anyone not directly involved in the exchange of data between two parties. There are two kinds of encryption, symmetric and asymmetric. Symmetric encryption is the simplest. Whenever you send a message, you scramble it using an algorithm, and you send the scrambling algorithm used alongside the message. When the recipient receives the message, they can use that algorithm to unscramble the message. This means that both sender and receiver know how to unscramble the message. But you can probably see the problem. It's easy to unscramble the message by a third party, because the algorithm itself is unprotected. This is why in modern computing, asymmetric encryption is used. This is when the unscrambling method is only known by the receiver. How is this done? Each party has a private key and a public key. When a message is encrypted by a public key, it can only be unscrambled by the corresponding private key. The public key is known by everyone, but the private key is kept hidden. When someone sends a message, they use the recipient's public key to lock the message. Now, until the message is received, no one knows how to unlock it except for the receiver. When they receive the message, they can use their private key to unlock it. A digital certificate is another network security method. It's basically an online passport that verifies digital identities. When you visit a website, the website presents their digital certificate to your browser, and if it is valid, your browser knows the website is legit. And if a certificate isn't shown, it's possible that the website is a fraud or impersonating someone that they're not. For the final topic of this video, let's go over the different cyber attack methods and how they're prevented. I know this looks slightly overwhelming, but when we go over them, I promise each of them will be self-explanatory. A distributed denial of service attack, or DDoS, is when a large volume of fraudulent requests is sent to overload and crash a server or network. These are very common, so there are a lot of tools dedicated to mitigating DDoS attacks. Alternatively, servers or networks can use VPNs or proxy servers to mask their true IP addresses or implement intrusion detection and prevention systems. Insecure network protocols are protocols that don't protect data when sent, which let hackers intercept the data. To address this, protocols use some form of encryption, and digital certificates, such as SSL or TLS certificates, are used to verify identities of data receivers. Malware is a general term for any software that's designed to steal data or crash devices. Since a lot of malware takes advantage of software loopholes, software should be regularly updated, like your operating system. Intrusion detection and prevention software, such as antivirus software, are also effective, while email filtering systems don't allow malicious emails to reach victims in the first place. A man-in-the-middle attack is when a third party taps into communication between two devices. This is usually the consequence of insecure network protocols, so the same solutions apply. Alternatively, senders can use VPNs or proxy servers to effectively hide and encrypt their internet activity. Phishing is when users are tricked into doing something that benefits a malicious entity. This can either be downloading malware or entering your personal information. Phishing is super common, and the techniques used by hackers are always evolving, so this is the one to look out for most in your daily life. Phishing is done mainly through email, so email filtering systems can help with this. And in case your information does get leaked through phishing, multi-factor authentication can help stop unauthorized access to your accounts. But mainly, don't be so trusting to everything you see online. SQL injection is when malicious SQL code is executed to manipulate databases. We'll cover these in more detail in the A.3 video, but simply put, databases are where data is kept, and SQL is a programming language used to query and alter databases and its contents. This is usually how data leaks happen, but hackers usually hold a lot more power if they can manipulate an application's data. To prevent this, input validation and content security policies are used to validate incoming SQL code, and intrusion detection and prevention systems prevent any backdoor access to databases. Cross-site scripting is like SQL injection, but for websites. Malicious code is put into websites before they are shown to users, letting hackers mislead users to do specific things, such as clicking on a link that they didn't want. Since this also involves the secret injection of code, the same prevention methods all apply here. Unpatched software is any software that has a vulnerability. Many big hacks online are at least partially caused by this, as it allows stuff like SQL injection or cross-site scripting to happen. Regularly updating software is key to patching vulnerabilities, while whitelists, blacklists, and intrusion detection and prevention software can prevent the access entirely until the vulnerability is fixed.
Okay, we're down to the last two. Weak authentication is when accounts are easy to breach into. This is why a lot of services have minimum password requirements or push you to enable two-factor authentication. Stuff like MAC address control or whitelisting and blacklisting can also control who can get through logins. Finally, zero-day exploits are when an exploit is abused without it being disclosed to the public or to the administrators of the system. The term zero-day refers to how the developers have 0 days to fix the exploit because of how it was unknown beforehand. To mitigate this, regularly updating software to patch vulnerabilities is important, as well as implementing proper intrusion detection and prevention systems.
And that's it for topic A2. Thank you for your overwhelming support that you showed me so far while I make these videos. I'm Jerry, helping you succeed in the IB. Thank you again for watching.